All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we will now begin. First off, good morning. I am Jason Thomas, Project Engineer with America Makes, and your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange webinar series, was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series coordinator, Jason Thomas, directly at jason.thomas@ncdmm.org. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we'll ask it during the Q&A session. We will do our best to get to all of the questions. Today's webinar is on defect detection limitations using CT scanning for additive components. Without further ado, it is my pleasure to introduce Rob Glassburn from 3D Engineering Solutions. Rob Glassburn holds a master's and bachelor's degree in mechanical engineering from the University of Kentucky and an MBA from Xavier University. Rob is a licensed professional engineer in the state of Ohio and has 25 years of experience in design, manufacturing, and quality roles across multiple industries. He holds 3 U.S. patents and is currently the Vice President of Operations for 3D Engineering Solutions. Rob resides with his wife and 2 children in the greater Cincinnati, Ohio area. Rob, I will now turn it over to you and your team.
Okay, thank you, and welcome everybody. I'll go ahead and just get started here. And again, be happy to take any questions that you have, but what we're looking at is what are the limitations in CT scanning for finding defects, especially for additive components here. Now, everything we're going to talk about also is valid for things other than additive components, but the focus is additive components here. So let me get started. Well, let me briefly state who I work for and what we do. We are an engineering services provider. You can see some of the services that we provide there and a little aged picture of our staff there, but a good one anyway. And more specifically, among the many different types of data collection equipment that we also have 4 on-site CT scanners. And our full staff is trained in their use. We have a NAS 410 level 3 up to that service we can provide for you. So we do a lot of different types of additive components, CT scanning, looking for defects, doing metrology exercises on additive components, troubleshooting those type of things, the whole gambit of things that you can do with CT. CT scanning, and you guys probably already are very familiar with this, but the basic idea here is that you've got a source of X-rays, and those X-rays pass through a part and hit a detector, a digital detector. The part, and that makes one X-ray obviously, the part rotates, and as it rotates, you're taking other X-rays. In a typical CT scan, you could have thousands of X-rays. We generally do over 3,000 X-rays per scan, per CT scan, and that just helps develop gives it enough information to develop the computation to get a nice voxel data set out of that. Well, of the defects that we're talking about for CT scanning and additive defects, what are we talking about specifically when we're talking about CT scanning? So these are some of the defects I found, I know about, and I found on the internet looking, and so these are defects I understand to be common for additive parts. We're not always looking for all of these in CT scanning, although we could for most of them. But predominantly, what we want to understand using CT are the ones highlighted by the arrows on the right there. And I've got a couple of things here that is kind of an overlap area where, yeah, you can use CT scanning to do it, but there are other technologies that could be looked at too. So we could use, for just looking at build shift or balling or some of these things, we could take a laser scan, a structured light scan of the area. We could use CMM probing. We could do lots of different types of scanning. But CT obviously gives the advantage of being able to see inside of the parts, inside of the materials, to look at potential structural issues that might be happening. If we'll go through the ones that we're talking about for CT. Trapped powder seems to be a common one. We get lots of these. The image that you see at the lower middle there is a additive part that we CT scanned looking for trapped powder. And lo and behold, there is some images right here of trapped powder. You can see clearly there's a channel designed in here, and there's a apparently less dense material. And it'll appear less dense, and that's generally what we see in an indicator of that. Let's see, start-stop issues. Didn't have a great single graphic for that, so didn't include a picture for that. But a lot of the other defects that we'll talk about could be, as a result of a start-stop issue in the build process. Hot cracking, that was actually a term I wasn't familiar with. I'm more familiar with just looking for cracks. Here's another image of a different additive part where we did find a crack, and it is actually an internal crack. It looks like, oh, this is the outside of the part, but no, this is an internal channel of the part, and here's a crack that was able to be found. It's a very visible, very obvious crack, and you can tell, the area around it looks very nice and clean, but we've got a nice crack going through there. Another thing that I'll show you, this is actually not an additive part. This is actually a composite part. We do lots of different types of parts, and here is right where the arrow is pointing, you can see some separation between the composite layers in them, and that is actually a crack right there, differentiated from the other blackish looking things that you see there, which is just a resin heavy area. And oh, by the way, here's some gas porosity that happened to be in this slide too that I'll just point out. Inclusions, so porosity is most typically asked for, that people generally want to understand, are there voids, are there trapped powder, are there, gas bubbles inside of there? But beyond material, the native material itself, you can sometimes get some foreign materials in there. This is actually another additive part, and what you see highlighted, arrow pointed to here, is actually an inclusion. It's actually a more dense material that somehow got into the build, and it shows up as a darker spot like this. These are all relatively easy to find for CT scanning, and one of the defects to look for. Porosity being, again, one of the more common things. This scan here, another additive part, kind of zoomed in here. I know this to be a pre-hipped additive part, and you can kind of see it has, I don't know, I call it, it looks like a Whopper. If you bite a Whopper in half, it'll look kind of like this. So you got lots of small porosity in here, but it's relatively even throughout the process. So whatever happened in this particular process, it was very consistent. So that's something to be said for consistency. Another example of porosity is from just a straight automotive casting here, not an additive part, but it does have a very nice image for porosity. It shows you a lot of the voids that you would see in it, and then surrounding those voids are very nice, clean looking material. A neat thing that you can do, and most of you probably already know this, is that you can visualize this porosity by making the surface of the part you're looking at transparent, and then seeing the porosity as small colored bubbles inside of here. And this one, this is probably that same composite part from before, and it just had a lot of porosity in between its different layers, and that's what's pictured here. All right, so now getting to the meat of things. What are the limiting factors in a CT scan to visualize and measure defects? We all want to know what's the smallest defect that can be found. And unfortunately, we can't just say, it's X size, it's this big is what you can find. It depends on a lot of different factors, and we'll spend most of the time here kind of going through those factors and getting an understanding of what's involved. This list of factors that I show here are the ones that we'll go through, and each one of them has an impact on what it takes to find and measure defects. And if you have outside service work done, or if you use internal resources, you'll run across the same thing. They'll give you the same questions about what the materials are, thicknesses, resolutions, those type of things, because everybody runs into the same problems. There are equipment-related issues and non-equipment-related issues, and we'll kind of go through those. But first off, material. So nice little periodic table here. I went ahead and circled some common metal additive materials. And next one I found out, oh yeah, some of these precious metals you can do as well in additive, which is nice. And just for fun, we'll do the plastics as well, which I'll call carbon for this purpose. Basically, the KV of a machine is kind of how powerful the CT equipment is, how much punching power it has to get through materials. And as you go up in atomic number here, that generally increases in density. Yeah, there are some exceptions, especially in these precious metals, like palladium is more dense than silver, and platinum is actually more dense than gold. But for the most part, for these metals that we're commonly dealing with, density increases as you go to the right, and that requires higher KV requirements, bigger machines, that type of thing. And this is just talking about, the same thing we just mentioned. Here are some typical scanner KV sizes. So if you have internal equipment yourself, or if you're using a service provider, they'll generally give you information like this. The first three KV values are more common equipment. You'll find those more often. They're less expensive machines. The bigger machines have higher equipment cost, obviously, to them, but the higher KV means higher punching power. For materials, for Inconel, high nickel parts, things of that nature, or copper alloys, you need higher punching power. There are also a class of equipment that is above 450 kV. I'll say 450 kV is the largest easily commercially available equipment that you can get. There are 600 kV units out there, and but they're still a developing standard. There's Comet makes a 600 kV gun, and there are some people who have them, but it's not very prevalent yet. Anything above 1,000 kV, 1 MeV, are all custom machines. And the real issue there is they have very great punching power, and they have some slight disadvantages, but they are one-off machines, and so you got to make sure the uptime is good, maintenance, some of those type of things you may have to be a little more concerned with. They could be down. The more common general equipment, the manufacturers have all of these things. They're I know for certain the ones that we have, they're very quick for servicing. We get service within a day or so, maybe 2 days, but it's very good. So if something goes wrong, they're there. If you're in dealing with this type of machine, it may take you a while, and maybe you can or can't handle that particular timing. All right, now I talked about that it was punching power, so let me give you an idea here, and these are just general numbers. So if I had a 160 kV system, I could probably get around 3/4 of an inch of steel, and you can see it goes up as you go to higher kV systems, but it is kind of an exponentially declining scale here too. So, if I've got a 225 kV system, if I went to 1 MeV, I would expect at least 4 times. Well, I don't quite get 4 times. I don't get 8 inches of steel, I get 5. So it is kind of a decreasing thing. And that's just the way it is, and it's just the typical limitations that are there. If you don't have enough punching power to get through, you'll get something that looks like this part. This is actually part of the part that we saw earlier that looked really nice, had a little porosity in here. But at the top here, we did not use enough KV to punch through, so this did not image well at all. And it looks a little cloudy and fuzzy. Well, for this particular project, they weren't interested in the upper structures here. They were only interested down here. So what we needed to image for the project was fine. However, this is what you'll find. In this cloudy mess of material, it's very hard to see any defect. If it's a very gross, overt defect, you'll easily see that, but otherwise you're not going to see probably what you're looking for. And again, just to emphasize that, even though we didn't have enough KV to punch through the very top, thicker part of this, the smaller area that we're our area of interest, no problems, data look great, everything looks nice. Just for another example, this is a part, not an additive part, but in a 6-inch wide aluminum parts, an automotive component, also has some steel and brass pieces in it. And you can see they appear as different shades of gray in the CT scan. Just to show, we used a different detector for this, and this is a lot of material to go through with a lot of different materials in it, and we were able to get a nice clean image to find defects that this customer was looking for. So that talks about material. Now accumulated thickness. Well, what is accumulated thickness? So it's not only the metal that the material is made of, but how much of it has to go through. So here's a slice of CT data that we have of a different additive part, and we're going to look at, some the idea that, as an X-ray goes through this part, it has to punch through each one of these walls, and this may be titanium if I remember correctly. It has to punch through each one of these walls and make it to a detector that's, sitting behind here. Well, with doing that, we have to take data all around the part. So we have to make sure that we get good detection on wherever our detector is over here as the X-rays go through the part. We want to get good, clean X-ray images. So what we have to do is when we're setting up the equipment, we have to set up the worst case thickness. What does that mean? We turn on live X-rays, we rotate the part until we find the hardest thing to punch through with KV, and then try to get a nice clean image with that. And what we end up doing is it effectively just adds all the thicknesses of the metal that you can see through here. And so, my example, and I'm just a guesstimate here, I think I'm about 43 millimeters. So even though I've got an OD of this part that's generally 90 millimeters in diameter, I'm only really punching through 43 millimeters of material. Well, so that's not, 90. So the size of your part is not really the issue. It's the accumulated thickness. To a lesser extent, the X-rays do have to go through all this air that's in between these channels, but it doesn't really get rid of X-rays or abate X-rays or detract from how many X-rays hit the detector. So that's less of an issue. Aspect ratio is another thing to consider. All parts are not shaped equally. So you may have, a very long part that's thin. I generally think of circuit boards having this kind of issue. And what happens is, when you're setting up the part, you have to set up for the thickest section, which in this case would be this long, thin part that we've got here. And it has to make it all the X-rays, enough X-rays have to make it all the way through to the detector to give a nice clean image. Well, when you do that, you have to turn your KV up so high that when you come in this direction, you end up not, let me back up here. You end up over penetrating, and it washes out the image. And I think I'll probably talk about that a little bit here. So you got the X-ray path, fully penetrate the path. It washes out the image when you go from this direction, and then that leaves you with, an issue that might look like the same thing that we saw here, where, okay, so not enough KV would be cloudy here. I actually don't have a good picture for washing out. Usually this occurs when we have multiple materials and we're trying to, image a metal and a plastic together. These are maybe co-injection materials. The classic example I remember is battery covers. So the car batteries that you have, they have lead terminals built into them. We had to CT scan some of those for a particular reason, and the plastic was gone when we imaged the lead, which seems like an odd thing to do, but every job's a little bit different. All right, part size. So another limitation to being able to visualize and measure the defects is part size. This should seem obvious, and a lot of these things are obvious when you think about them, but you've got to be able to put the part in the scanner, right? So they make CT scanners now, desktop small scanners that these are probably close to $100,000 or so. And they have bigger scanners like this one. What you also have to worry about is the height of the ceiling, right? So I can put a pretty big part in here, but I got a ceiling to this at some point. We get a lot of requests for parts that are very long, and we might see, oh, we could scan the width and the thickness of it, but it's so long it hits the ceiling of our unit, or just doesn't work for a reason like that. Another option for CT scanning, and this is something to keep in mind, if you have a very long part, like this part sitting here, which I think is actually a helicopter blade, you can take your some of your things to medical CT scan operators. They will actually do things after hours or when they don't have humans in there, and they'll scan your parts for you. And these, obviously, the parts don't rotate. The scanner rotates internally. And it's okay. They're not as nice as the industrial CT scanners. I don't believe they're as accurate. They're not calibrated. There's some things that are not as nice about medical CT scanners. But obviously, everything has to fit in order to scan your part. So here's one of our CT scanners, and just another thing, the source to the detector distance, right? So over here on the left is a 400 kilovolt source, and on the right is a panel detector. There's actually another detector behind this panel, but there's a dual detector system here, and the part has to fit within this window. So if it's wider than that, one, it won't fit, and two, the part has to rotate. So it has to not only be just barely fit in there, it has to rotate through there as well. So that could be problematic. The detector size is also a limiting factor for the part. So obviously, if you have the X-rays are hitting the detector, if you've got a tiny detector, you're not visualizing very much of the part. This is just a representative picture of a Perkin-Elmer panel, which is the largest single panel, I believe, that you can buy. This is a Varian or a Varex panel from one of our smaller machines. And just to show you just a kind of a size difference there. Another technology that might give you a little more room is a panel shift technology like shown in this picture here. So in this one, the panel takes an X-ray image here while the X-rays are on. The panel will shift over, take some more X-rays over here, and then you will start rotating the part. And it kind of continues doing that. It's kind of a longer process because you're taking many more X-rays, but it gives you much bigger window, and you can make more use of this one detector. So you're adding more time, but you're able to image larger parts. And there's kind of just an image of that. So if I say, oh, this little symbol over here is my X-ray source, and these green lines are the array trace of two of the X-rays coming out that hit the edge of this detector that I have here, I can fit this particular part inside of here. And I have, quote, large detector. So if I had a smaller detector, well, the X-rays are probably still penetrating up here and just hitting the back of the cabinet, but the small detector, I can only really visualize what's going on here. That's not necessarily bad, and we'll talk about that in a little bit, but it's just a limitation of size that could impact what your ability is to measure, detect, and look for defects. And another obvious thing is this is a manipulator from that same machine I showed you before. The part, can't weigh an infinite amount, obviously, and so our manipulator is good to 100 kilograms, 220 pounds. So if it's much heavier than that, we're not going to be able to. We're not going to put it on there. We don't want to damage our manipulator. So that's a limiting factor there. Well, what does that really mean in the end? In the end, as a general rule of thumb, I'll give you this number. This number is not always perfect. Ours are actually a little bit bigger than this, and some might be smaller depending on what detector they have and such. But if you can fit the part into a 9-inch tall, 9-inch diameter, didn't put the diameter symbol, cylinder, then you should be able to do it in one CT scan. And that's a pretty common standard. Most folks will be able to do that. And you can also take advantage of height. All the stages generally move up and down. So if you've got something that's 18 inches, twice as tall, well, that's a couple of scans. Well, maybe not quite 18. We want some scan overlap sometimes. Unless you're using a helical scanning system, we have that type of system. And some manufacturers use software to do that as well, so there are other ways to get at that. Let's see, on those size of the parts, here's just another, okay, so you got a part that's bigger than the 9 inches, what do you do? Well, here's that secondary detector from the one machine we showed you. I can do about 20 inches. This is a linear detector, a curved linear detector in this case, but it's only taking one line of images at a time versus a panel here that takes a whole panel of images at a time. But this one with the panel shift, I can get over 20 inches. So it gives you a lot more flexibility for larger parts. And you know, these are available. You can find these. Different service providers have them. If you have CT scanning internally, they may have that as well. So it's something to look at. Partial volume scan. This is related to the size thing that we were talking about. So if I have a bigger part and I really only care about a small section of it, I may choose to do what's called a partial volume scanning. And there's a couple of reasons to do this. The biggest reason is for magnification that we'll talk about later. But basically what happens is the X-rays that hit the detector are only the ones that fully go through the part as the part rotates 360 degrees around will be imaged, as a nice 3D CT scan. And you can see I've got the little blue lines here. Those are actually part of it. What's down here between the green line and the blue line, you're not going to get good data there. And I'll show you some images of part we've done this way, just to show you what it looks like. But again, the idea is I've got an area of interest. I don't care what's happening up here or down here. I just need to know what's happening here to a better detail. By using partial volume scanning, you can do that. You can image the defects to a greater extent, magnify them, and see more things going on. Now, this is a part that this is actually an additive part as well. It was bigger than, it's a partial volume scan. And so you can see areas here where, oh, it looks beautiful, it looks just like the part. Well, if you knew what the part looked like, it would look just like the part. And up in here, you see the same thing. Looks great, no problems. But what is all this garbage here going around the side? Well, a partial volume scan will virtually draw a cylinder around your part equal to the scan volume, if you will. And everything that's outside of that area, outside of here, will be represented by basically noise. And that's what you're seeing here. All this stuff here is noise. This part actually has projections that stick off of it, but because you're not looking at the entire part, but only a subset of the part, it can only image, the part that it can fully see 360 degrees around. So the advantages here is I can get, a higher magnification of something, or if the part's just too big to CT scan all the way, I can still CT scan it. The negatives are I got to contend with this garbage on the outside here, so none of this is going to image well. And even in some of this inside part here, it's going to look pretty bad as well. And you may not be able to detect porosity or some of the crack defects, those kind of things that you're obviously looking at. And you can see it's very characteristic. You can see these vertical lines here. It's clearly not part material. There's also something going on here. And if you're internal guys or an external service that you use, if they're very proficient, they understand, they know what characteristic noise is, and they can point that out to you and distinguish it from actual defects. All right, so let's see. This is the same thing that we just talked about, noise. And so the stuff on the outside is just noise. But again, it can be easily detected. Resolution. This is the one that'll take a few minutes to go through. There's several slides on this. It's an important thing. It's something you always want to look at. You always want to ask, what resolution were you able to get? Because it's not always 100% clear what the resolution is going to be before you actually start. And, it comes to the question of what's the smallest defect that I can see in a CT scan? That's the base question that we want to talk about resolution. Well, generally speaking, to get better resolution, or to get a smaller defect size, able to visualize that, you need better resolution. There are, of course, other factors involved, but resolution is inversely related to defect size. You want small defect size, you need a much better resolution, which might mean you have to go partial volume scanning or do some other things that we'll describe here in a moment. What determines resolution? Well, there are three major factors that determine resolution here, and we'll go through each one of them. Spot size, magnification, detector, pixel size, a pitch. Two of these, the first and the last one, are equipment related. Whatever equipment that you have to use, or if you find an outside source, that determines what they can do spot size-wise and detectors. They're not buying a new source for your project or a new detector. Those are quite expensive. They're not going to do it. Magnification is something that is specific to your project, the size of your part. If you have smaller parts, you'll get better magnification. And you'll see the effect of this as we go through the slides here. Spot size, what does that mean? And what is it? So again, I'll use my little graphic to show it up here again. Here's the spot image of the source, right? And here's the detector. What you really want is you want the smallest spot that you can get. And the values generally, when you hear about this, they'll be from a little less than a micron to over 1,000 microns. And I'm showing 3 different graphics. And I asked somebody to review these slides for me. He goes, oh, I love that the larger graphic looks more fuzzy, you know, because that's generally the association. The larger the spot, the harder it is to get sharper images. You still can, and it depends on what you're looking for and the size of what you're looking for. So smaller is better in this case. So for my analogy, what I'm going to use is I'm going to say, hey, my source is a flashlight, right? Photons, X-rays are photons, and we'll go through there. So if I put an object, some squarish shaped object in here, into my detector, I'll say is this brick wall in the background. When I shine a light over this object, it casts a shadow on the background here. And so that is this is related to spot size. So this is my analogy that I'll start with. If I add a second flashlight here and let it cast its shadow, you get an overlapping square on the brick wall here. And what I'll say is, you know, the distance between these flashlights, we'll call that the effective spot size. So what's happening here, though, is they don't both line up, and you get somewhat of a fuzzy image. You know, this square by itself looks great. The other square by itself looks great, but you overlay them together, and it's kind of fuzzy. So go to the next one here. Yeah. If I move these flashlights closer together, the little fuzzy area becomes less fuzzy. And you know, this is also called geometric unsharpness, is the more technical term for it. So if I flip back and forth here, you can see, more fuzzy, less fuzzy, based on the spot size. So the smaller the spot size, the more sharp the data will be. And there are exceptions, and some objects you're forced to use machines with very large spot sizes, and you can still get pretty decent images, but just know this is a limiting factor for determining defects. Here are some specific examples. I said it was 1 micron about to 1,000 microns. And so R1, this is using data from ours, right? Our 160 source is about a micron, maybe a hair less. Our 225 machines are at about 3 microns. Our 450 is at 80 microns, which happens to be the best, and it is kind of the standard of the system, or the best that you can get. More typically, you can find 400 micron spot size, 450 kV systems. But traditionally, they're all about a millimeter or so. And I've even heard of them 2 millimeters, 1.5 millimeters. So they can get very big, depending on how many MeV they are. You know, these are, you get a much bigger machine with much bigger spot size. So magnification, next parameter we want to look at, using my flashlight brick wall example again. If I move the part closer to the wall, you saw that the square shrunk. Okay, so I demagnified it effectively. And if I go the other way and pull it closer to the source, it magnifies the shadow that is cast on here in my example. And so you can see, so I want the object as close to the source as I can get it. And what I've tried to do here with this picture is I tried to keep most of this square inside of these lines, because if I go further, then part of my part is outside of the lines. More of that partial volume effect we were talking about, or partial volume scanning. So just keep that in mind. And whoever does your work for you, they're going to make this magnification as big as possible. And there's a reason for it. You know, if you look at the different magnifications I've just shown you and overlaid them, and if you think my brick wall here, each brick is 1 pixel of your detector. Well, what you're really trying to do is you're trying to spread out the number of pixels or bricks along this pattern. So on my highly magnified part here, the biggest image here, I count 8 bricks in this image. My medium, I got 6 bricks, small ones, 4 bricks. So what does that mean, really? What it really means is, make sure I've got another one here, is a higher resolution. So I've got, this length has never changed, right? The object length is the same, but I'm describing it with more pixels. That means my resolution is higher. And in CT scanning, resolution and accuracy are directly tied together. So the better resolution I can get, the better accuracy I'm going to get in the end. So you want that not only for resolution, you know, as we're talking about here, but for accuracy as well. Can we use smaller bricks would be a first question I would think. And yeah, the answer is yes, but there is a limit, you know, that you can use. And so the detector matters is the next part of this, right? So in the system, we have detectors, and let's represent it by a grid like this, for example, right? This is my X-ray detector. It's made up of this grid of how many cells that are. And what I'm going to do is I'm going to take an X-ray image of something. And this line here is this line is the virtual shape of the part, okay? And so the X-ray is seeing material here, which will show up as one color, and air here, which will show up as another color. And what this detector is actually doing is it is actually assigning a grayscale value to it. And I'm going to say, air is at 15,105, and that's just a made-up number. The material here is at 45,300. And so what happens is each one of these pixels that go through the actual part shape has some fraction between these two numbers, between air and material. And this is a way that it's going to look at what is the material and what's not, or it's later used in CT scanning for that. If I take it and say, well, I'm going to make this little stair step in here and call that stair step material on this side and fully air on this side, we know it's not. That's only sort of the case. That's what you can say. So if I took the same material, same image, but made my detector pixels smaller, I might be able to do something better with this little stair step. And you get the idea. I've got more resolution, more pixels, so I can make the stair step closer. And it's kind of this effect that we're talking about. So by doubling my pixels, making the pixels half as big, I've increased the resolution by 4 times. So let me show you a picture of one of these. This is an X-ray of another additive part here. I zoomed in on this area and I'm showing it here. You can see the pixelated little values here. And so where in this view it looks like, the solid blacker areas are very clear and defined. Well, no, they're kind of fuzzy. It's not clearly, here's clearly material. Well, somewhere in here's the edge, right? And here's clearly less material or a different material. And that's just a brief summary. There are more factors involved in that, but that's for another webinar, another time. We can talk about those things, or I'm happy to answer questions if there happen to be questions related to that. Number of pixels, or number of voxels in a defect. So number of voxels. So now if you understand resolution, what is the smallest defect I can reliably find? Well, what we'll tell you is generally 8 voxels large. It doesn't mean anything to you right now. And most folks will say that. Anything 8 voxels large, and we'll describe a voxel in a minute, is something that we can distinguish from background noise and from other noises that happen. What's a voxel? A voxel is a volumetric pixel. Here's pictures of voxels here. Have you ever seen the game called Minecraft? That's all voxels. And that's what CT data turns into be. It turns into a voxel data set. Millions of cubes that know their location, know the size of the cube, and know a grayscale value that represents density or the ability to abate X-rays. Why 8 voxels? Well, because it's a rule of thumb. And it's over experience and long periods of time to understand, yep, when I know I have at least 8 voxels, then I'm good. Well, there's another piece to that. It can't be just 8 voxels, but more generally, to be assured, you want the 8 voxels to be closely packed together. They're all strung out in a line like this. That could still be noise, or it becomes less detectable, harder to really understand what's going on. Let me give you another example, a picture of something like that. This is CT data, and you're looking at a slice of data, and you're looking at the effect of something that's been 1 frame averaging versus 128. We'll describe that a little bit later. But with only one X-ray of information per frame that was used here, you see these dark, blacker spots. They could be voids, right? There could be, something going on there. It could be like that one part we saw above that I said looked like the inside of a Whopper, if you like that candy. But if you take the same part and you do a lot of averaging for it, it looks very clean. You don't see anything distinct, nothing black. It doesn't look characteristic of a void. And it looks like, oh, this is just more characteristic noise that happens to be in all CT scan data. So having a larger number of voxels, you can be assured that your void is a void. So there is a defect detection limitation. We will say 8 voxels or larger, and well, how big is the voxel? That kind of depends. We'll talk about that here in a little bit on how big a voxel you can get. Well, or how small a voxel you can get. That's magnification related. We'll talk about that in a moment. Multi-material samples, not as applicable for most of the additive parts that we're measuring, but if you put your additive parts in an assembly and you want to check it after some cycling or some stress that you put on it, this may become something you want to contend with. Well, what is the effect of multiple parts? Well, this is a plastic part with metal components in it. I think this is also a different type of metal down here. So what you're really seeing is multi-material. And the idea is we wanted for this one to image the plastic part really well. The metal was less of a concern, but we get these artifacts, these little streaking artifacts. The part is not really shaped like this long disc of things. And the real problem with that is if you zoom in here, you don't know what's happening in this area here, because this is probably all still artifact from streaking. So if you're looking for a detail or defect in here, you may not find it, or you may not be able to clearly find it. You can use higher KV on this part and image just the metallic in this case, but when you do that, as we said before, you'll probably blow away all this plastic lighter material. So everybody who's doing CT is always balancing conflicting things. And so telling whoever you're having do the CT work for you what you're really looking for, what your parameters are, will help them greatly, because then they can save you time and money by doing these kind of things. Again, it could hide areas of interest in here, and that's a look at multi-material stuff. Time. So time is a factor that nobody has enough in. Everybody who comes in here wants everything yesterday. That's a pretty common thing, and my answer is, you want it by noon yesterday, and the answer is yes. So time equals quality. So the more time you can put in a CT scan, the better quality data you're going to get. The less time, the less quality. If you're doing, just a few parts, spend the time. You'll get the best quality. If you're doing production volumes, still spend the time early on to define what your smallest defects that you really need to find are. Then you can back the quality off and still make sure you can see the defects. And so with time, you get more time yields more quality. I should have wrote the axes on here, but the quality improves, but the benefit diminishes with more time to use. Here's another frame averaging example. Frame averaging helps with that. This is one frame, 128 frames. So one frame is much quicker to do than waiting for 128 X-rays of something. But the quality is much nicer here on these artifacts. You can read between the lines here. Here is a lot of speckle, a lot of noise. It's just much harder to see. Beyond number of frames, you've got the exposure. And what the exposure is as a CT setting, it's the amount of time the X-rays are actually going through the part and allowed to accumulate on the detector before the next image has to be taken, before the part rotates the second time, and then more X-rays are put. On our machines, we generally have control between a quarter of a second to 4 seconds for exposure time. 4 seconds is a lot if you're doing lots and lots of projections or X-ray images on there. Let's see, number of projections. This is the other thing here. So what you're doing here is you're slowly rotating the part as you're taking X-rays and it's accumulating on a detector. Like I said, we typically use over 3,000 X-rays to do our scans with. It gives us a very nice, clean data set. It does take a little longer. I know in production, I've heard of folks using only a few hundred, 400 or 800 projections. And again, Once you've defined what you really need, then you can cut things back, make things very quick if you've got large production volumes. But, so I say the number of projections is 1 to some high number, some higher number there. If we take our voxel data set represented by this cube, and if we look at just one slice of that, what we're going to see in the next thing, we can see the effect of different numbers of projections. And this looks like kind of like an eye chart to me when I look at it. So, and actually the guy who reviewed it for me said, hey, put some red lines around those pictures because it looks really confusing. And so if you look at our one slice of data here, what you're seeing is, well, if we only used one projection, CT would reconstruct this to look just like this screen. So, and we know the part's going to look like this in the end, right? So if you use 2 projections, okay, I'm starting to see a shape. There are 2 shapes now, and looking more like this. 4 projections, you can start to see what's going on. Still got a little noise over here, but after 1,000 projections, wow, it's very clear what's going on. So that's the effect of using a smaller or larger number, and that's a time factor that we're talking about here. Another image that shows that is this one. These look a lot more fuzzy, and this is, 1 to 64 projections, and the fuzziness is really for a different reason. What they use when they reconstruct these is they're using back projection, and this is called unfiltered back projection. The scan quality of the picture I put in here is not great, but it is unfiltered. Up here, these have nice, clear, sharp, distinct lines. That's a filtered back projection. They've applied a formula to it to sharpen up the edges and to make the blacks blacker. And so you can see, like in the back here, oh, it's still kind of fuzzy. It's not as black. Well, maybe it's as black. It looks as black, but it's generally not as black as the background here. So let's go. So here's an example of timings, right? So we talked about exposure, number of projections, and then the frames. And the frames, again, I may not have explained it originally, but it's how many of each projection you take. So if I rotate the part 400 times, taking 400 X-rays, I'm actually taking multiple of those X-rays. So I'm not going to do one because we showed all the noise that happens when you only have one frame. And so I can increase the number of frames to improve the quality. I can increase the number of projections, increase the exposure time. But it has a direct impact on scan time. So here I show you 4 examples. One's only 3.6 minutes. The longest one is 32 hours that I show here. We've done scans here that have gone as quick, full CT scans as quick as about 3 minutes even to about 150 hours. So 150 hours is a long time. You're not going to do lots of parts like that. It gets very expensive. But 3 minutes, you can do a lot of parts. So it all depends. And again, it's all understanding what defect you're looking for and what you can get away with. Subvoxel accuracy, probably the next question you're going to ask is, hey, wait a minute. The voxels determine where the edges of the data are. So, does that mean the voxel size is the limit of accuracy? No, that's not it at all. So modern software can do much better than that. And what you see here is a rendered view. It's called surface interpolation activated. This is in volume graphics. And this is a rendered CT slice that you're looking at, and it looks relatively smooth through here. That's not actually what the voxels look like. The voxels actually look like this. So the voxel, as it's created, reconstructed, look like this. So the distinct edge is not very clearly related. So how do they do that? Well, what they do is they do surface determination, and they figure out where they think the surface is in between. And the way they do that is they look not only at the voxels themselves, but they look at neighboring voxels. They may even go out very far and look at voxels out here and voxels down here. And they also look at voxels in both directions as well. They understand that surfaces in reality are continuous. So if they've determined the surface is right through this brick, well, this next voxel here, it has to be continuous, so it has to at least start there. And they use formulas and formulations like that to determine the surface. So you can go from a nice clean surface like that from something, the original voxel set that looks like that. So very distinct, very good improvement. So let's see what we got here. We talked about that. Well, how accurate can you get? Generally, everybody says, within a third of a voxel, you should be able to locate where that surface is. The president of Volume Graphics told us directly, says, I'm very confident to 1/10 of a voxel. I don't know if everybody believes that, but he certainly does. He made the software that most people use. So If we look at one of our little voxels here and we say, hey, this particular voxel has a edge that's 21 microns in size, by magnification, you got it to be 21 microns, then the accuracy that I can determine where that surface is, I should be within about 7 microns of that. So that helps in understanding the shapes of the defects that you've got, and here's our little simple formula to show that. So, well, that makes an assumption of something here. That assumes that this 21 microns we said that our voxel was, that you actually believe it's 21 microns. Well, what is that plus or minus, right? So what is the accuracy of our ability to size something in CT? That brings us to metrology. And it's a key factor. It's really a newer factor for CT scanning. Traditionally, CT scanning is visualization only. They want to see a pretty defect or see something, but we're getting lots of requests for understanding the size and distribution of the defects and the size. Because, I guess when you're doing structural analysis, it's not only the number of defects, but how big they are, how closely they're spaced, and being able to know for certain that they're of a certain spacing is important. So, what size defect can you allow is another question to ask. And most of the folks who come to us, they've not yet established it, right? So we see a lot of brand new parts that are just being able to be made, and they're trying to replace existing parts with additive, and they don't know what the limit of the defect that they want to see. And the general answer is, well, how small can you get me, And, well, that's the question. I can get you very small. You might spend many hours or a few days CT scanning to get that, which costs a lot of money. So if you can at all understand how small a defect you actually care about, that helps tremendously. If you can't, we can still help you. It just may cost you more because we're trying to give you the best, cleanest image that we can, and that just takes time. And as I said, these are new applications that are, so people don't understand the sizes that they actually need. Go ahead. No, sorry, thought there was a question. We'll get that here in a second. We're pretty close to done. CT scanners now have our metrology grade in some cases. This one is one of ours. It has a CMM scale on the back. So it helps you determine the magnification more precisely, which gives you that assurance. It's actually listed on our ISO 17025 scope. Another way to do it beyond using metrology grade equipment is to use traditional type of equipment, but put artifacts in with them, like these ball bars here, or take the part and measure it on a fixed CMM. There's a picture of a scale right there. And then, compare it to the CT data and scale to that. And these are scaling artifacts used to check for calibration of our equipment. And here's another artifact down here. So there are many ways to do it, but be very careful. It's always important to ask, right? Because you don't know what the other side, if you're doing an outside source or even your internal resources, what they're doing to calibrate their machines. I have truly heard of people calibrating with tape measures, and you wouldn't trust that very good for accurate sizing. The pictures are still going to be correct always, but the size is really what we're talking about here. Here's just some numbers from one of our, two of our CT machines have this, and then we use, for our standard equipment, we'll use just artifacts, and then we calibrate it to other equipment, CMMs, that kind of thing, just so we can be assured of the number that we're showing you. The very last two slides are some extraneous things. I thought, oh, these are really cool. People want to see this. This is a newer module in VG that shows finding the number of cells. So a lot of stuff we get from additive have a lot of cells inside, and they want to know how big are the cells. Well, there's software functions that'll let you know that. And even more importantly, they'll show the distribution of those cell sizes, or in this case, strut thickness sizes. So if I want to know all my struts, are they being made accurately, and what size am I getting mostly, and what am I actually yielding? So here's a curve, a histogram, showing all the different strut sizes and colorizing it. So medical guys are really interested in this. They're looking at stuff for bone ingrowth to make sure that, it's the optimal parameters to ensure bone ingrowth. And they want to see, how much is actually to what my CAD model or my original model was. So that's the end of my presentation here, and I'll give it back to Jason to see if there were any questions at all during this.
All right, thank you, Rob. We will now head into the Q&A session. If you do have a question for the presenter and you haven't done so already, please type it into the chat box and I'll ask Rob. I do have a few questions here to start. Our first question is, what is the difference between a void and unmelted powder?
Oh, very good question. So a void and unmelted powder. So sometimes there could be very little difference, and sometimes there could be, you know, a lot of difference. If I go, let's go look up here. Let me just scroll up way up here. I'll be a quicker way to do that, but I'm just going to do it the slow way. So we had a picture at the very beginning that showed some powder in there, and we will see, what you generally see is a shading difference is the real answer. Wow, it's way up there, isn't it? A lot of slides here. Get up there. And a little further. There we go. Nope, a little further than that. Be nice about it. There I go past it. All right, let's see. Oh, here we go. So if you look here, you'll see we've identified this as a powder, you know, right, unmelted powder. And I should, if I could zoom in a little closer, what you would see is that the powder looks a more dark color than the clear wall that's next to it. So the wall is more fully dense material. The powder is less dense because there's a little bit of air in between. And that's what you're doing in CT scanning is you're looking for density differences. And so if the powder were very tightly compact, it might look exactly like a thick wall. But generally, we don't find that in powder. We find the powder to be a little lighter in color. And so a void would be more like the black area around it. And that's generally what you see is more black area. Now, if your spot size of your equipment is so large that it's kind of distorting very small voids, you may not notice that. You may think it's a little bit of powder versus a void. And so sometimes it may be indistinguishable. And it's a kind of a spot size, geometric sharpness issue that can happen there too. But in general, powder will look just less dense than the surrounding walls around it, minus any artifacts that are in the scan. The voids will look darker, and you might see a combination of both. So you might see, you know, a start-stop issue, and you know maybe it turned power off for a little bit, and it just left powder there, and it covered it over. Well, that would just seem a little lighter, or there might be a little bit of darker area and a little bit of lighter area. So hopefully that answers that question a little bit. If not, please ask again, and I'll see if I can refine that answer.
All right, thank you, Rob. We did have one other question. I think I can handle that one. Someone asked, is it possible to get a copy of this presentation? So if anybody is interested in this presentation or any of our other TRX webinar series presentations, they are available on the America Makes YouTube page, and this one will be posted in the next couple of days. So let me see if I have any other questions here. Let's see, I think we do have some. All right, what was the reference ISO for calibration, or the referenced ISO for calibration?
Sure, yes. So what we've got here is our lab is ISO 17025, and that's a metrology, metrology and calibration reference for ISO. It is the standard that if you go out for outside inspection services, we are a certified inspection service, you'll look for this standard. So if you want somebody to do CMM work for you, for example, you want them to be ISO 17025. Because it means several things. One, they're audited on a yearly basis. They have to do proficiency testing. They have to develop what's called measurement uncertainties for all of the values that they measure. And those are important things, especially for when metrology matters. And a lot of people don't do this. This is kind of a pain in the neck, right? Because it's a lot of paperwork. It's a lot of understanding, a lot of time. And there's expense involved in it. But it is highly critical. And for CT scanning, we've had customers who had requirements for ISO 17025. Mostly automotive have that requirement. A lot of others do too, or they should have it. And they'll come to us because we're one of the few service providers who happen to have that and in a CT machine. Other providers can do it as well. They just haven't spent the time, money, and effort to make that happen. But hopefully, in a nutshell, that's what it is. And this is the reference that you want to look for, ISO 17024, for any of your inspections, CMM, laser structured light, CT, any of those things.
Okay, so let's see. We have another one here.
What is the process for integrating defects info from CT scans into existing CAD models or FEMs?
Okay, very good question. So when we take a CT scan, it is as a voxel data set, and I don't have a really picture for that, but I'll show you the voxel when I get to it. So the voxels are a bunch of cubes, and they represent the density and the location and size of things. Well, what we can do inside of the software that we use volume graphics, is we can take that voxel data set and turn it into an STL file. STL file stands for stereolithography. It's a triangulated file, and we can take all of the internal defects, make STLs of those voids or inclusions or things, and then export them from volume graphics. Those are importable into CAD. They're a little hard to work with, but they are importable into CAD. You can do things with them. You could model around them if you want. We do that type of work all the time. It's just part of our business. But yeah, so we can take the voxel data set, turn it into an STL file, export those STL files, and you can import them into your CAD. What you want to ask us to do, though, is actually what you want to do is give us your CAD, let us align it to the voxel data set, and then export it. That way, when you pull it into your CAD, all the defects are in the right area.
All right, we got another question here. Have you ever used a penetrant to identify hairline cracks that could be x-rayed and show the crack?
Excellent question. So this is a question involved in how small of a crack can you find. And so CT scanning is one of the non-destructive measurements, NDT measurement methods. And the thing you got to realize about each of these NDT methods, not one method does everything. Our level 3 CT guy will say, yes, CT is good for everything, jokingly, but certain cracks can get so small that they're undetectable. And they're undetectable by the parameters that we talked about. So it's the voxel size. What's the smallest voxel size that I can get, and that determines my crack? Well, if you think about a crack, cracks initiate from solid material and they grow to some size. So obviously there's going to be a size where it's hard to detect, even for penetrants. But you don't. That's a pretty small one. Penetrants are very invasive. They do a very good job on it. So comparing the two, again, I want that 8 voxels worth of open crack. When I have that, depending on your voxel size, then I can be reasonably assured, yep, there's the start of my crack. I could look at that area once I find that and speculate and see where a crack comes to almost a beginning or 0 point, and those are for internal defects. Now, obviously, the limitation with penetrant is it's on the outside of the part. So if I've got cracking on my inside of the part, there's no way I can use the penetrant to really see it. I suppose you could bathe it in penetrant, put a scope in there and kind of look for it. Maybe that's done, but that seems very difficult to do. So in those cases, you're limited to whatever CT can visualize based on those number of voxels. And again, it's that give me a good 8 voxels worth of data, and then I can be assured that, hey, it's not noise, background noise, or characteristic things that happen in CT. But yeah, there is an excellent question. Not one NDT method is great for everything. So CT scanning has its place, looking for internal cracks. Can't really do it with the liquid penetrant, but the liquid penetrant is going to find stuff on the outside to a higher degree. That's always going to be the case. But if you're going to CT scan anyway, because that there's going to be stuff potential on the inside for all the channels that you've got working through there, might as well look on both inside and outside of the part with the CT scan. You can always go back later and do penetrant as well. So that's my answer. Hopefully I've answered the question well. If not, please refine the question. I'll be happy to try again.
All right, so that's all the questions that we have. That will wrap up today's TRX webinar series. I would like to once again thank Rob. If you have any further questions for Rob Glassburn, please reach out to him directly at rglassburn@3d-engineering.net. And Rob, if you want to go to the last slide so that they can get a good view of your contact information, please.
Absolutely.
All right, thank you. There will be a post-webinar survey going out to all of those who participated. We do really appreciate the time you take to provide America Makes feedback so we may continue to improve and strengthen the additive community. And as a reminder, if you think you or your organization would be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation or reach out to myself, Jason Thomas. Thank you very much. Have a great day.